So welcome back, and today we'll start with the module 5, that is Z transform, and more oftenly we'll pronounce it as Z transform. Z is pronounced as Z transform. Okay, so that is module number 5, and this is just a replica of what happened for continuous time signals. That is, we'll just uh, go back a little while. That is, go back a little bit backwards. That is, we have learned about continuous time signals, that is Fourier series, that was for periodic signals. And then for a periodic signals, Fourier transform was evolved from Fourier series, and we have seen that also. And at the end we have seen that for some signals Fourier transform does not exist. The reason was that the integration was not converging, or the integration was leading to infinity. So if that leads to infinity, then such an integration was not converging, or we can say that Fourier transform for such signals does not exist. Okay, so again, so why did the Fourier transform did not exist? Why that happened? Why that signals that didn't have that uh, Fourier transform? The reason was that, see, when t tends to infinity, that signals also led to infinity. That was the reason. So as time goes to infinity, my signal also goes to infinity, or the signal itself is an unbounded is an unbounded signal as t tends to infinity. And that was the reason why Fourier transform for such signals does not exist. So uh, for solving such things, or to find the Fourier transform of such signals, we have added, or we have multiplied a convergence factor. I hope you remember that convergence factor. That is, the convergence factor was e raised to minus sigma t. So that as time t tends to infinity, this factor e raised to minus sigma t tends to 0. So it will pull back the signal which was going towards infinity towards 0. So that is the advantage of having such a convergence factor e raised to minus sigma t. So we multiplied that, and we evolved a new operator, that was Laplacian operator S. Okay, and so that Laplace transform was evolved from Fourier transform, and this was the main concern. Laplace transform was evolved from the main concern that for few signals Fourier transform does not exist because the integration was not converging. So that was Laplace transform, and we have seen that in Fourier transform the integration was confined to the j omega axis, but in Laplace transform it was confined to an entire S plane. Okay, so inside, anywhere in that S plane, that is in if we pinpoint, that is, if the region of convergence is specified for any signal inside that region of convergence, at any points inside the region of convergence, that integration will converge. And that is why we always tell that we have to specify the region of convergence also along with the answer of Laplace. When you find the Laplace transform of a continuous time signal, we have to specify the region of convergence also, otherwise it is meaningless. Since if it is not specified, then you cannot say that many signals have Laplace transform in the entire S plane. Only one case is that is impulse function, where Laplace transform will exist in the entire is a S plane, that is ROC is the entire S plane. For all other signals, ROC should be specified. Why? Because in such points, ROC, within that ROC, or at any points inside the ROC, the Laplace transform exists. Outside that, Laplace transform also does not exist. That is why. So there is naturally a question which arises: if we have a Laplace transform of a signal, will it have a Fourier transform? So answer was also specified in few lectures earlier. That is, when you find the Laplace transform, you are specifying the ROC also. So if the ROC includes the j omega axis, then such signals will definitely have Fourier transform. I repeat, if the ROC includes the j omega axis, even if you're standing with the Laplace transform, if you when you see the ROC, if it includes the j omega axis, then and there itself you can tell that, confidently tell that this signal definitely have Fourier transform or Fourier transform exist. Or if a signal has a Laplace transform, you have specified the ROC, and if the ROC does not include the j omega axis, straight away you can tell that such signals does not have Fourier transform, or such that it is for such signals that Laplace transform came into existence, because Laplace transform came into existence only because some signals does not have Fourier transform. For such signals, Laplace transform was evolved, and that is why we use the Laplace transform for such signals. It is for such signals that we have evolved Laplace transform. So in the same note, we can tell that is for the Laplace transform. What if Laplace transform was for continuous time signals, then for discrete time signals it is Z transform. So discrete time signals also have Fourier series. We'll see that in the last module. Discrete time signals also have Fourier transform. We'll see that also in the last module. So for Fourier series is for periodic discrete time signals or periodic digital signals. Fourier transform is for discrete time. Fourier transform is for aperiodic discrete time signals. And some signals does not have one minute. Some signals does not have Fourier transform. Some discrete time signals does not have Fourier transform. For such signals, again, just like what happened in Laplace transform there, for such signals we multiply that Fourier transform with a convergence factor, so that there it was integration, here it is summation. For discrete time signal is always summation, it's not integration. Okay, so why Fourier transform does not exist for such signals? Because the summation does not converge, or the summation will lead to infinity. For such signals, we are evolving a new transform that is in parallel to Laplace transform, but only the difference is that it is in discrete time domain. So Z transform is for discrete time domain, discrete signals, whereas that is digital signals, whereas for continuous time signals we have Laplace transform. So we'll see that is there are few signals. So you can, on the sidelines you can see a statement written with blue ink, that is x of omega, that is a Fourier transform of digital signals, that is in summation from n is equal to minus infinity to infinity x of n e raised to minus j n omega, that is actually the Fourier transform of x of n. So if this summation does not converge, then you can straight away say that Fourier transform will not be existing for such signals x of n. So for that signals, Z transform is the solution. So Fourier, it is from the Fourier transform again that Z transform is evolved. So how will you evolve the Z transform from Fourier transform? The only difference is that is along with x of n e raised to minus j omega n, you multiply a convergence factor, that is r raised to minus n. So you can tell from here itself that if r is 1, then 1 raised to minus n is 1. So the thing is that for Fourier transform, r is taken as 1. So for Fourier transform, r is taken as 1. That is why 1 raised to minus n is 1, and that is a similarity between Z transform and Fourier transform. Okay, so what is that r? R is actually a radius of a circle. Okay, so r is the radius of a circle. So if r is 1, then that becomes a unit circle. So why it is called a unit circle? Such a circle is having a radius 1. So for a Fourier transform, the radius of that circle is a unit circle. So for Fourier transform, we moved along that unit circle, just like the Laplace transform. In Laplace transform, we moved along the j omega axis. Here for Fourier transform, we moved only along the unit circle. Okay, but as in general, r can take any value. So depending upon the radius, the circle enlarges or shrinks. So you can see that the circle will be covering the entire z plane. So just like what we have seen in Laplace transform, where it was S plane, here we have Z plane. So instead of confining our attention to simply the unit circle, we are having a liberty to vary the radius of that circle so that we can cover any regions of that z plane. So that's a difference. So we have more freedom, or we can bring, or we can find the Fourier transform of many signals if we multiply that with this convergence factor, that is r raised to minus n. Okay, so if you take into account, so we just take the same equation, that is what I have written in the right left hand side in the side lines. There is x of j omega summation from n is equal to minus infinity to infinity x of n e raised to minus j n omega. That much is already there. With along with that, if you multiply r raised to minus n, and from that, if we take a minus n common, you can write it as summation that is implicitly written. That is, it is understood that that is the limit of summation is from minus infinity to infinity. So that's why it's not written there. So summation from minus infinity to infinity x of n r e raised to j omega the whole raised to minus n. So that r into g raised to j omega, r into e raised to j omega is simply z, or the operator. Okay, now substituting that again, we have the final definition for z transform, that is x of z is equal to summation from n is equal to minus infinity to infinity x of n z raised to minus n in general. Why in general? Because depending upon the signals, the limit of summation can change. For example, if you have a causal signal, that is what is a causal signal? The peculiarity of a causal signal is that it is multiplied with u of n. So if a signal is multiplied with u of n, that is strictly causal. That is, it's a strictly right-sided sequence. So if you have a right-sided sequence, then your summation will be from 0 to infinity. Okay, or if you have a strictly anti-causal signal, your limit of summation will be from minus infinity to minus 1. So that is what. Okay, so what is a similarity? What is the similarity between z transform and Fourier transform? Fourier transform is nothing but the z transform is nothing but the Fourier transform of a new signal, that is x of n r raised to minus n. Okay, that is initially you had only x of n, then you purposefully multiply that with a convergence factor r raised to minus n. So what is z transform? Z transform is nothing but the Fourier transform of a new signal, that is x of n r raised to minus n. Okay, so naturally there is a question arising, that is, I told that what is the existence of z transform? The absolute summability and square summability were sufficient conditions for z transform to exist. That is again one more thing. Okay, here also ROC is very important. That is, within that ROC region of convergence, this summation will converge, otherwise it is not. So there also the question of existence is also there. That is, within the ROC, this summation will be converging, otherwise not. Okay, so why it is otherwise not? Because otherwise this signal will not be absolutely summable. Okay, so that is a preliminary things which I have to tell in comparison with what we have learned in the continuous time signal. Okay, I hope you have got the crux of what is z transform and why it is different from Fourier transform and why it came to existence from Fourier transform. Because the thing is that some signals does not have Fourier transform. So Fourier transform, we moved along the unit circle, but here we have the liberty to move within the z plane by varying the radius of that circle. Okay, so there in Laplace transform, if the ROC included j omega axis, then Fourier transform for that signal existed. Whereas here also in the same note we can tell that is if the ROC includes the unit circle, then that signal will have Fourier transform also, otherwise not. Okay, that's a preliminary thing which we have to see. So we'll see few problems also just to understand. Okay, before going into that, what is ROC? So region of convergence, I told that it's a collection of points. Okay, it's a collection of points within the z plane where the summation will converge. Okay, so in general you can tell that this region of convergence for z transform is an annular ring between two circles of radius r suffix small r and r suffix small l, that is r large and r small. Okay, r, it's not r, it's small, it's actually rs actually. So rs is actually, s stands for small, So RL, it's a large circle, and RS is nothing but the small r. Okay, so you can, in general, you can type, it's actually hashed there. So in that hashed portion is actually the region of convergence, which is between two circles of radius RL and RS, where RL stands for R large and RS is nothing but R small. That's a small circle, and the other is a large circle. So how much can be the maximum radius for R large? The maximum radius of R large can be up to infinity. And how small can be RS? RS can be small as 0 also. That is, RS can be confined to origin. Okay. So RS can be as small as 0, and RL can go up to infinity. So that's the limit. That's a boundary condition. Okay. So we'll see few problems. So there also we started with the impulse function. Here also we start with digital impulse, that is x of n is equal to delta of n. So by definition, instead of x of n, we can substitute delta of n. We know that delta of n exists for only one value, that is n is equal to 0, and the value is 1. Okay, so the entire summation is only existing only at one point, that is at n is equal to 0, and the value is also 1. So n is equal to 0 means z raised to minus z raised to 0 is 1. This delta of n also has value 1, so the result is 1. And irrespective of the value of z at any points of z, the value is 1. That is why we can tell that 1 exists for every value for z. So z plane means a point in z plane is nothing but a point in the, okay, that is the point in that inside the region of convergence. So that is the meaning of z plane. Okay, so 1, it's all 1 for every points inside the z plane. That means we can tell that ROC is nothing but the entire region of convergence. There also we have seen that for continuous impulse, we have seen that the Laplace transform existed for all points in this plane. Here also for digital impulse, Z transform exists for all points in the Z plane. Okay, so here you can tell that RS is equal to 0 and RL is equal to infinity. Okay, typical example where boundary condition is satisfied. Now take the next example, another very simple signal and very common signal, that is x of n is equal to u of n. Okay, I told that depending upon the nature of the signal, the limits of summation also change. So when you substitute here, the summation limit will be from 0 to infinity. U of n will have all values 1 from n is equal to 0 to infinity. So that is 1, and simply we have inside the summation z raised to minus n. Now just we can write z raised to minus n as z raised to minus 1 the whole raised to n. Now a question will arise, why we are writing that in such a form. We have a just inside the box over there, you can see that it is in the form, now it's in the form of a geometric progression. That is, in general, summation from n is equal to 0 to infinity a raised to n is nothing but 1 by 1 minus a. So just to write in that form, we have written it as z raised to minus n the whole raised to n. Okay, so if you write that, then it can now the a value is z raised to minus n. Now instead of a, we have z raised to minus n. So if you substitute that equation for that geometric progression, it becomes 1 by 1 minus z raised to minus 1. Also before that, see that summation again, that is summation from n is equal to 0 to infinity z raised to minus 1 the whole raised to n. Now when will that summation converge? That's a big question, and that question should be answered, because that will specify the region of convergence. Simply performing Z transform does not mean that at every point in the Z plane we have that Z transform. You have to know the points inside the Z plane where the summation will converge, and that is what is all about the region of convergence. So how will you specify the region of convergence? So that's specification, or that ROC is specified by what is happening by that by summation. When so who decides the convergence of such a summation? The convergence of the summation is decided by the value of z raised to minus 1. Why? If z raised to minus 1 is greater than, suppose if z raised to minus 1 is 1, what happens? 1 raised to n. So n value are varying from 0 to infinity. So 1 plus another 1 plus another 1. Likewise, you are adding once infinite times. You are adding once infinite times. So what is the result? It's infinity. So you can't have z raised to minus 1 as 1. Can you have z raised to minus 1 greater than 1? It's not possible. sorry, z raised to minus 1, if z raised to minus 1 is okay, so that's the thing. So you cannot have that value as 1 either, or you cannot have the value greater than 1 also. If that is greater than 1, 2 raised to 1 2, 2 raised to 2 it is 4, 2 raised to 3 it is 6. Likewise, if you substitute it as 0 raised to minus 1 as 3, again the same thing happens. So you cannot take any values from 1 till infinity. If that happens, then the entire summation will blow off, or the summation will lead to infinity. So definitely for the summation to converge, then 0 raised to minus 1 should be less than 1, or the magnitude of 0 raised to 1 should be less than 1. If it is equal to 1, again that will lead to infinity, and if it is greater than 1 also, that will lead to infinity. Okay, so magnitude of 0 raised to 1 will decide the region of convergence. So you can write this as, that is 1 by 1 minus 0 raised to minus 1. I can write it as, what is 0 raised to minus 1? That is 1 by z, that is 1 by z. Okay, if you substitute that, that becomes z by z minus 1. Okay, so the thing is that the region of convergence is nothing but mod of z greater than mod of 1. Why I'm specifying it as mod of z greater than mod of 1? What is z? If you go a little bit upwards, what is z? Z is nothing but r into e raised to j omega. So if mod of z means we are finding the mod of r into e raised to j omega. R into e raised to j omega. So e raised to j omega, we know what is e raised to j omega. It is cos omega plus j sine omega. So what is the magnitude of cos omega plus j sine omega? That is root of cos square omega plus sine square omega, that is 1. So magnitude of e raised to j omega is 1. So that entire thing will have a magnitude of r. So that means we are actually specifying the magnitude of the radius, and we know that radius is always positive. You just see that radius, that is the radius of that unit circle which is drawn inside the z plane. That is whether it goes to the second quadrant, third quadrant, radius is always positive. Whether the circle is inside, the part of the circle is inside the first quadrant or fourth quadrant, or in the second quadrant or third quadrant, radius is always positive. So that is why we always specify that mod of z. Mod of z means the mod of radius is, that is why we specify mod of the radius itself. Okay, so that is why region of convergence is nothing but it is specified by, here we have 1 here, that is why we have mod of z greater than 1. So for u of n, you can tell that the region of convergence is outside the unit circle. Okay, and the region of convergence is outside the unit circle means, that is, you have written that as that mod of z inverse less than 1 is the region of convergence. From that you can write as mod of z greater than 1. That is, outside the unit circle means this region of convergence does not include the unit circle, meaning this u of n does not have a Fourier transform. Okay, I hope it is clear. Now, what is RS? What is a small circle? Small circle is nothing but it is the unit circle, that is 1. And what is the radius of that large circle? It is infinity. Okay, I hope this problem is very clear. If you understand this problem, it is very simple. Now, the third question, that is alpha raised to n u of n. Now, if you simply substitute the value of, instead of x of n, you can simply substitute alpha of n, and you can change the limits of integration, which will consider u of n, that is limits of summation will be from 0 to infinity. And you can take n outside, inside the bracket that will be alpha z raised to minus 1, the whole raised to n. Now the similar case itself, there the summation will converge only when mod of alpha z raised to minus 1 is less than mod of 1. This summation, the same situation, this summation will converge only if alpha z raised to minus 1. There it was z raised to minus 1 only because there was no coefficients. Here we have another coefficient, that is alpha. So alpha z raised to minus 1 should be, mod of that should be less than mod of 1. So mod of alpha z raised to minus 1 is nothing but what? Radius multiplied with alpha. Okay, that is okay. Mod of alpha is z raised to minus. We know what is z. Okay, z mod is nothing but r and e raised to j omega, that is mod of radius itself. So that radius is being multiplied with alpha. So mod of alpha z raised to minus 1 should be greater, it should be less than 1, mod of 1. That should be the condition for the summation to converge. Okay, and so we'll keep that in mind. And if you substitute that same argument, that is here also a raised to n, you can apply the geometric progression here also, that if you apply that, that will that is nothing but 1 by 1 minus alpha z raised to minus 1. If you substitute for z raised to minus 1 as 1 by z or 1 by z, you will get it as z by z minus alpha. And we know that the region of convergence was mod of alpha z raised to minus 1 less than 1 or less than mod of 1. Radius is always positive, so you can write it as 1 also. Okay. So if you simplify that, you can write it as mod of z greater than mod of alpha. So earlier problem for u of n, the ROC was outside the unit circle. Here you can tell that it's not the unit circle there. The radius is alpha. It's not radius 1, it is alpha. That is why I told that radius is being multiplied with, if it was only u of n, the radius was 1, and that is being multiplied with alpha. So alpha into 1 is alpha. So now the radius is alpha. So the ROC is outside this circle of radius alpha. Okay, now what is RS, the small circle radius? It is alpha. What is the upper circle radius, larger circle radius? It is again infinity. So one thing you can confirm, for any right-sided sequences, that is a sequence multiplied with u of n, ROC will be outside the circle. It can be circle of unit radius, or it can be a circle of any radius, which can be alpha. Alpha can take any value. Okay, in general, for any right-sided sequence or for a causal signal, you can tell that region of convergence is outside the circle of radius r, where r can be any value. It can be alpha, it can be 1 or any value. Okay, then another situation, I told that a signal will have Fourier transform if the region of convergence will include the unit circle. For u of n, we have confidently declared that that does not have any Fourier transform. Why? Because unit circle was there, the region of convergence was outside the unit circle, so region of convergence is not including the unit circle, so that does not have any Fourier transform. So what about the third problem, that is alpha raised to n u of n? We have seen just before us, we have the region of convergence, we are seeing the region of convergence which is outside the circle with alpha radius. So the question is, will this signal alpha raised to n u of n have Fourier transform? Does this sequence have Fourier transform? The answer is that you cannot tell yes or no here. The answer will depend on the radius alpha or alpha value. If alpha is less than 1, if alpha, suppose it is equal to 1, but what happens? The same situation of u of n will come. Okay, that is the region of convergence will be outside the unit circle if alpha is equal to 1. So again, you can tell that for if alpha is equal to 1, it is equal to u of alpha. If it is equal to 1 means, what about the sequence 1 raised to n u of n? That is again u of n itself. Okay, so alpha value, if the alpha value is less than 1, then such a signal will have such a signal will have Fourier transform. So that is a condition there. For such a signal, Fourier transform will exist only depending upon the value of alpha. So what should be the value of alpha? Alpha should be less than 1. If the alpha value is less than 1, suppose if alpha value is 0.5, then the region of convergence will be outside 0.5. So outside 0.5 means unit circle is also included within the ROC. So that means such a signal will have Fourier transform. Okay, so we'll be taking another question here, that is find the z transform of r raised to n cos n omega naught u of n. You simply substitute by definition, you know everything. Keeping the results of alpha raised to n u of n, we can simply write that is cos n omega naught. How can you write that? So cos we know, that is cos n omega naught is nothing but that is r also I take outside. So cos n omega naught is nothing but e raised to j omega plus e raised to minus j omega by 2. Okay, so if we take r also inside, you can take n also the common outside. So we'll write it as half will come outside. It's nothing but the z transform of, incidentally we're finding the z transform of r raised to n cos n omega naught u of n. Okay, where cos n omega naught can be written as e raised to j omega plus e raised to minus j omega by 2. So that 1 by 2 will be coming outside. Then e raised to, sorry, one more thing. Cos n omega naught is nothing but e raised to j n omega plus e raised to minus j n omega by 2. Okay, so if we take r raised to n also inside, half will be coming outside. So inside the bracket, r e raised to j omega the whole raised to n plus similarly r e raised to minus j omega the whole raised to n. Outside we have u of n. Okay, so individually we can apply the principle of superposition here also. That is, half will come outside. We are finding the z transform of r into e raised to j omega the whole raised to n u of n plus half z transform of r into e raised to minus j omega the whole raised to n u of n. Now this each term is typical to alpha raised to n u of n, where alpha for the first term will be r into e raised to j omega. For the second term, alpha will be r into e raised to minus j omega, only differences. So we'll be utilizing the result we have found earlier. So for that, instead of alpha, we are writing e raised to r into e raised to j omega, that's all. So half will be coming outside. It is nothing but z by z minus r into e raised to j omega, close the bracket, again half into z by z minus r into e raised to minus j omega. Now what about the ROC? ROC is the same. There it was alpha, mode of alpha, mode of z greater than mode of alpha. So here also what happens, that is mode of z greater than mode of r e raised to j omega. So mode of r e raised to j omega is nothing but what? Why we have taken that? Because earlier it was alpha, mode of z greater than mode of alpha, or mode of magnitude of alpha. Here instead of alpha we have r into e raised to j omega. So this mode of z greater than mode of r into e raised to j omega. So mode of r into e raised to j omega is simply mode of r, because e raised to j omega magnitude is 1. Okay, so the question is answer we have got. Only thing remaining is we have to simplify that. You just simply go through that simplification, and finally we can write the answer as 1 minus r cos omega z raised to minus 1 by 1 minus 2 r cos omega z raised to minus 1 plus r square z raised to minus 2. ROC is specified, mode of z greater than mode of r. In the same way, similarly, you can solve r raised to n u of n sine n omega naught. Answer also have written, ROC is also written. You just solve that and do it as a homework. So with that, I conclude my lecture, first lecture in Z transform. Understand the basics, understand the definition, try these problems. Okay, thank you.